Okay, so if you want to find the exact values of theta, where theta is an angle that lies somewhere between 0 and 2 pi. So someone from 0 included round to 2 pi excluded. And all we know is that the sine of the angle is a half. And we know, so this is our angle going in. And this is a ratio coming out, a ratio of two lengths. And we know that the sine, the ratio is, we say it's the length of the y leg divided by a radius r. So if sine is positive, that the radius is never negative. So if sine is positive, we must be somewhere in the top half of this circle, okay? Because it must have a positive y. We know our y must be 1 and our r is 2. Now, if we're asking you for an angle, then the only angles we can ask you about are quadrantal. And if it's quadrantal, or a quadrantal angle, either your x or y, the legs, one of them will equal 0, or one of them will equal the same length as the radius, okay? So this is not quadrantal, because that y isn't 0 and it doesn't equal 2. So it must be able to draw a triangle. And the only triangles we can ask you about when we're asking for angle are 30, 60, 90, or a 45, 45, 90. And the legs in a 45, 45, 90, we say the legs. So one of these will be x, one will be y. They can switch around. Those are 1 and 1. And the r in a 45, 45, 90 is the square root of 2. The 30, 60, one of this could be the x, or it could be the y. This could be the x, or it could be the y. One of them, the legs, is of length 1. The other one is the square root of 3. And the radius opposite the 90 is 2. So if the radius is 2, this is definitely part of a 30, 60, 90. It is not 45, 45, 90, because that would have had an r square root of 2. So that's 1 is the short leg. If the y is the short leg, I'm looking at that angle there and that angle there. That y is 1, that y is 1, that r is 2. And the third leg, if I needed it, the x leg, would be the square root of 3 over here and negative the square root of 3 over here. But what the actual question is asking me for is the angles. So I want this angle here and this angle here. Now the angles are based on this reference angle of 30 degrees. If my reference angle is 30 degrees, which is pi by 6 in radians, I have one answer in quadrant 1 and one answer in quadrant 2. In quadrant 1, with a denominator of 6, the numerator is just pi. In quadrant 2, with a denominator of 6, the numerator is 5 pi. So those are my two answers, pi over 6 and 5 pi over 6. Okay? Those are my two answers for an angle where the sine of the angle is a half. Right, so that was a warm-up to really warm us up for what we're going to do today, because what we're going to be doing today is we're going to be doing unit 4.6-1, which is inverse trig functions. So what do you remember about inverses? If you're live in class, I would ask you now to turn to your neighbor and name 3 things you remember about inverse functions. So all of you, go to your window and yell out into the wide world to your neighbors 3 things you remember about inverse functions. No, don't do that, or the police are going to be called, because everyone thinks that you've all gone nuts. But let's see, what can you remember about inverse functions? Do you remember why we need them? Inverse functions help us to solve equations. If you have something squared and you want to get rid of squaring, you square roots. If you have something added, then you subtract to get rid of it. If you have multiplying to cancel out multiplication, you undo it with division. So that's what inverse functions do. We need them to, they undo each other. We need that to solve equations. And to find the inverse of a function algebraically, we switch the x and the y, and then we solve for y. What practically, this is a very important concept. If you have an inverse, a function and its inverse, the domain becomes the range, and the range becomes the domain. That's your x and y switching. That's why that technique with algebra works. That's really important, though, that the domain of your function becomes the range of your inverse function, and the other way around as well. Okay? A function has an inverse that is also a function if and only if it is one-to-one. And to make it one-to-one, you might need to restrict the domain. We're going to go through an example of that in a second. And you know if it's one-to-one if it passes the horizontal line test. Okay? So let's have a look at what we put some of this into context. Looking back at the warm-up, the sine of theta equals 1/2, we were actually solving for theta. So we want to do something called the inverse sine of theta to get an angle. Now the angle we got as our answers, we got pi by 6 and 5 pi by 6, and we did it using triangles, but we could have maybe done it using the graph. Here's a graph of y equals the sine of theta. Okay, the sine has a range from -1 to +1. It's this wave, and we wanted to know whether sine was equal to 1/2. So where's a half on here? There. It's like this horizontal line going all the way across here. So where do those lines intersect? Well, this is on this axis here, your x-axis, we're actually plotting the angles, theta. There's whatever this angle is, this angle, this angle, this angle, intersect there, intersect there. This was where we found pi by 6. This was our answer here of 5 pi by 6. And we only went up to 2 pi. So we stopped there. So we didn't choose this answer or this answer, and we didn't go backwards. This would have been -7 pi by 6. This would have been -11 pi by 6. We only chose those two answers because we were given this restricted range. Okay? But there would have been, as an answer to this question, if we hadn't been asked to restrict the range, there would have actually been an infinite number of answers, because this wave keeps on going on and on and on forever. But look at this sine function. Remove all my scratchy work. Is it a one-to-one function? It's not one-to-one. It fails this horizontal line test. We put a horizontal line across where y was equal to 1/2, and we got multiple solutions. If we're going to do the inverse sine of the sine of theta, we're only allowed to have one answer, not two, or not a million, or not a billion, or infinite number. So we're going to have to restrict that function in some way so to make it one-to-one. Let's look at something you're more familiar with. X squared equals 4. If we graph that function, it would look like this. Here's the graph of y equals x squared. 1, 2, 3, 4. It's not one-to-one. It fails the horizontal line test. I just put in there the line y equals 4, and it actually has two solutions. Okay? If we were solving this algebraically, how we'd undo that squared is we would take the square roots. And that would give us the answers, x equals plus or minus 2. Here's your answer, x is -2. Here's your answer, x is 2. But this graph is not one-to-one. That's why when we do this problem on a calculator, we don't get that as our answer. On a calculator, we only get the answer x is positive 2. Calculators can only give us one answer to a problem. They can't give us two answers. If we were on inverse trig, they certainly couldn't give us an infinite number of answers. Now, why does the calculator only give us one answer, and why does it choose this answer and not -2? The reason is, if a function is not one-to-one, we have to restrict, write this idea of what we're doing now is what we're going to apply to inverse trig. Please write these notes. We need to restrict the domain of y equals x squared and to make the graph one-to-one. How we choose to do this, it's become a convention and it makes sense to us. We choose to just get the right half of that graph. That's from x values of 0 to infinity. We choose to restrict the domain from 0 to infinity, which now the green part of that graph is one-to-one, and now it has an inverse that's a function. Okay, that would be the graph of y equals the square root of x, and that's a function. It passes the vertical line test. We could have, if we were crazy people, have chosen to choose all the negative values, but why would you choose negative values when you could choose positive values instead? It makes sense for us to choose the positive values, and that's what your calculator does. It gets y equals x squared, just looks at the domain from 0 to infinity, and then creates the inverse of it like this. And that's how it gets the one answer, x equals 2. And we're going to have to do something very similar when we do trig functions, because none of our trig functions are one-to-one. And we have to work out how are we going to restrict that domain so that we only get one answer. First of all, let's look at our how we write things. How would I write in math? How do we write the inverse of a function? How do we write the inverse of function f of x? Now, if you try to type it into your keyboard, it's a little tricky, isn't it? Just typing it in without some special way of formatting your text. To put this little -1 up there is actually quite tricky. But that's what we mean. That's how we write this. This says, in math language, that says the inverse of function x. And it can get a little confusing because this looks here, this looks like an exponent. But it isn't an exponent. Exponents are very different from inverses. So look at that. X to the power -1 actually means 1 over x. When this is the exponent there, that's an exponent, the answer we get is the reciprocal. And in math, an inverse is not the same thing as a reciprocal at all. So when you see what looks like the power -1, you have to understand it in context and say, are they asking me for the inverse or are they asking me for the reciprocal? Okay, this here, that means the inverse function, inverse of function f of x. This, written this way, means the reciprocal of f of x, 1 over f of x. They're different things. If we take the sine function, I hope you know the reciprocal of sine is the cosecant. This This one here means 1 over sine x, which means cosecant of x. This is not an exponent. This is how we write the inverse. That means the inverse of the sine function. So that means we're getting a sine function, and this is how we would solve it. This input, think about it. We normally take the sine of something, and something comes out. And if we're going to do the inverse sine, what goes here and here are going to reverse. It's like you saying you switch your, I don't want to say switch x and y, because that becomes very confusing when we're talking about sines and cosines, because we use x's and y's to mean something different. We're going to switch the domain and the range. Okay, so the domain is your inputs. Think about what goes into a regular sine function and what comes out. Now, this stuff I'm drawing here, please write this out very neatly, the space around it, so you can come back and look. Because if you don't understand this part, you're going to get very lost on this unit. These notes right here are really important. What goes into a sine function? So I can write neatly what comes out. Well, an angle goes in. Your input is an angle, and what comes out is a ratio. And we picture that as the ratio of two lengths, sides of a triangle, or a distance away from an x or y coordinate compared to a radius. And for sine, it would be your y divided by your r, so ratio of two lengths. So when we're doing the inverse sine, when we see inverse sine, yeah, somebody's got a question for me? We have a quiz on Friday. Inverse sine, you switch your inputs and your outputs, your domain and range switch. The ratio is going to go in and the angle is going to come out. So when you get a function and its inverse, the domain and the range switch. So we're going to do some questions in a second. We first of all have to look at how we're going to restrict the domain. Because if I drew a sine function, okay, it's not one-to-one. Definitely not one-to-one. We have to think about how we're going to restrict it. So let's get that first, and then we can do some actual questions with it. So in your notes, quickly just sketch a sine wave. It doesn't have to be beautiful. This is just to actually just pick up the understanding of what we're going to do. For the inverse sine function, we have to restrict the graph, restrict the domain to make it be one-to-one. We could be crazy and we could say, oh, okay, I just want part of the graph and I've got to go all the way from somewhere where it's going all the way from the bottom to the top. You could be nuts and you could choose that part. Would it be very conventional to choose between -3 pi over 2 and -pi over 2? No, that would be ridiculous. We don't do that. The part we choose to use is somewhere around about 0. So if I went from there to up, okay, that's covering the top half of my graph, but I also need the bottom half as well. So I'm going to have to go backwards a bit there as well. We're going to write this note's very important. We restrict the domain of sine. So we're restricting the angles from -pi over 2 included to +pi over 2 included. And we can do the same for the cosecant. Cosecant, remember, would have an asymptote here, and the graph would have half of a frown here and half of a smile here. For cosecant, theta. We're going to restrict it from negative pi over 2 to pi over 2. But look, there's an asymptote in the middle which has to be excluded. Okay? That's how we're going to have to restrict our domains for sine and cosecant. Let's have a look at the cosine function. How would you restrict a cosine graph to make it 1-to-1? If we did the same as we just did between negative pi over 2 and pi over 2, that's not 1-to-1, still failing the horizontal line test, so that won't work for us. On a cosine graph, to make it be 1-to-1, we're going to start at 0 and, okay, that will go all the way from the top to the bottom. That works for us. We're going to restrict the domain of cos of theta for angles between 0, this is your angles, and pi. Which means for the reciprocal, secant, the secant graph has an asymptote there, half a smile, half a frown. We still can go from 0 to pi, but there's an asymptote at pi over 2, which kind of has to be skipped. Now there has to be, there's no way you can just remember all that. Well, you could. It'd be very boring to have to remember all that. You need to know these restricted domains to answer any of the questions at all. So let's find an easy way of doing it. If I put this on a circle, going all the way from 0 to 2 pi, I would be starting at angle 0, which is here, and going around there to pi. So that's like the top half of the circle. I'm not going to give any answers that are in the bottom half, okay? So I'm going to be working with only quadrant 1 and quadrant 2. How would that work with sine? If I look at what I've got then, put those angles on a circle for sine, going from 0 to pi by 2, and 0 down to negative pi by 2, and not using any of these angles whatsoever, that's like the right side, the right half of the circle, right half. And this is quadrant 1. And I don't want to call this one quadrant 4, because if I chose an angle and I went to it thinking it was in quadrant 4, I'd be kind of going through this part. And I want you to think of this part here as a sea full of sharks. If you go through this part here at all, you're going to die. Okay? So I don't want to think of that as quadrant 4. I can't die, it won't work. I want you to think of that as quadrant -1. To get to any angle down here, we're going to have to come down to it, not go around the long way. Okay? That's the right side of the circle. Let's have a go at doing some of these problems. Okay, here's 3 problems, and this is how to do them. The first thing you do is you notice that this is not a sine function. See that -1? Just remind yourself, as soon as you see this is a trick, right? Equals theta equals. Reminding yourself my answer I'm going to be giving is an angle. Okay? Then you ask yourself, will it be in the top half or the right half? And you have to remember for each one of them, which half of the circle. Some of them you're restricted to just answers in the right half. Some of them you're restricted to answers in the top half. Now there's a way to remember that. Just get the words sine and cosine and try to put them together like a crossword puzzle. It doesn't work if you put sine there. That doesn't link to cosine. But it does if you write cosine across the top and sine down the side. Now can you see how that's your circle? Cosine is in the top half and sine is in the right half of the circle. That's a way to remember which ones go which. And that also works with secant and cosecant. Secant, cosecant. Secant uses the top half from 0 to pi. Cosecant goes from negative pi over 2 to pi over 2, the right half. Okay? Right. So when we get a question, this is the first thing we do. Recognize that it's an inverse. We're going to write an angle. Then ask yourself, top half or right half? Well, sine is right half. Draw this picture, and now you've got a possibility of 1, 2, 3, 4, 5, 6, 7, 8, 9 answers. There's only 9 answers that it could possibly be. We're asking you for an angle. We don't give you a calculator. We can only ask you about quadrantal angles or angles based on 30, 60, 90, 45, 45, 90. Okay? Now rewrite your question as a regular sine function. So switch your angle and your ratio. So say we're looking for sine of my angle equals 1/2, and I know that ratio for a sine is y divided by an r. I know it's not quadrantal because the y isn't 0 and it doesn't equal the radius. So I know I'm going to be drawing either a 30, 60, 90 or a 45, 45, 90. And if y is 1, that's the short leg of a 30, 60, 90. So my reference angle here is 30 degrees. And I want to name this angle here in radians. That angle is pi by 6. Okay, I've picked out that angle because I know the y is the short leg of 30, 60, 90. Okay, let's do the next one. You know, if you're trying to type that in, you try to type it in now, just without any special font. To type in sine to the exponent -1 was impossible just about on an old-fashioned typewriter with no manual. This is the old-fashioned way before Microsoft Word and word processors. This is the old-fashioned way of writing inverse sine. And it's quite nice because the A at the front reminds you that you're looking for an angle, okay? But this just means inverse sine of 1. So I know that 1 must be a ratio because that's what a ratio goes in, an angle comes out. I'm actually looking for the angle for which this is true. If that's a ratio, it must be 1/1, must be y over r. And before I do anything else, I ask myself, sine, inverse sine is the right half. I'm going to draw that picture and say which of these angles going through which of these points, does my y equal 1 when my radius is 1? Well, if one of the legs is the same as the radius, this is quadrantal. So we've drawn a circle, not a triangle. We're not going to draw a triangle at all if it's quadrantal. And we're just thinking a circle of radius 1. If this is a circle of radius 1, where on there does the y coordinate equal 1? This point has an x of 1 and a y of 0. This would have an x of 0 and a y of -1. This one has an x of 0 and a y of 1. It's this angle here that is pi by 2. And my third problem here, I'm being asked for the inverse cosine of -1/2. I see that inverse, immediately write equals theta equals. It reminds me I'm solving for an angle, okay? I want to know the angle whose cosine is -1/2, where this ratio must be the cosine, that's an x divided by an r. That would be true in 2 quadrants, but we're going to be restricted for inverse cosine. Inverse cosine, cosine, like this, top half. It's negative. Where would my angle be, where would my ratio be negative? Well, everything in quadrant 1 is positive, so cosines are going to be negative in this quadrant. So I know I'm looking in quadrant 2, and I'm looking for the triangle where the x, oh, that's the short leg of a 30, 60, 90. If x was the short leg of 30, 60, 90, I'm at that angle there. Where that reference angle is 60 degrees, which in radians is pi/3, but I'm not in quadrant 1, so what do I call that angle? With a denominator of 3. When I'm in quadrant 2, the numerator is 2 pi. It's 2 pi/3. Okay, I've done 3. Now you have a go at doing a couple yourself. Try those. So first of all, you see all of them are in inverse. So as soon as you see inverse function, remind yourself the answer is going to be an angle. Then ask yourself top half or right half. Think about how cosine and sine go together. Anything that's to do with an inverse cosine is going to be top half, top half. Anything to do with the inverse sine, I'm just going to look at angles that are in the right half. Okay? Now it does really help to rewrite out the question and switch your domain and range so you can just write a regular cosine function. Cosine of our angle is 1, and that must be a ratio of x divided by r, so make that be a ratio. The first thing I notice is the x is the same length as the r, so I know it's quadrantal. So I am not looking for a triangle. I'm just using a circle of radius 1. And I'm looking for the point that's got an x coordinate of 1. Well, that's this point here. So now I have to name the angle. If the name of this angle going through that point, we could call it 0, or we can call it 2 pi. If you call it 2 pi, you've gone around there, and you've gone in the sea of sharks, and you've died. It's too big. Remember, our angles are restricted somewhere between 0 and pi, so I have to call this angle 0. To call it 2 pi is unacceptable. This one, cosine of inverse cosine of -1 will be an angle somewhere between 0 and pi, and just rewrite that as the cosine of some angle I don't know yet is negative ratio, well, that ratio is x over r. Again, it's that same idea, it's quadrantal, but this time your x is -1 on a circle radius 1. You're just thinking that in your head. So that must be this point here. This is the point -1, 0. But what I want, remember, this was reminding me, I want the name of the angle. The angle that takes me there is pi. And for this last one, I want the angle whose sine is -1/2. It's negative. sine of my angle is negative 1 over 2, and that would be a y over an r, definitely not quadrantal. Anything positive would be in quadrant 1. If it's negative, it's going to be down here somewhere. So that is part of, it's not a 45, 45, 90. That would be wrong, because that has a radius of square root of 2 if the leg is 1. Okay, so it must be a 30, 60, 90. So what I'm thinking in my head is a 30, 60, 90. The y, that 1 is the short leg. Is it that 60 or is it that 30 there? Which one of those has got the short y? The one with a reference angle of 30. So it's that angle there. My reference angle is 30 degrees, which in radians is pi by 6. Now I just have to name that angle. Again, we cannot call it, so it's something, this name of this angle is something divided by 6. You cannot call it 11 pi by 6. You went through this part here, you're dead. No, that's wrong. Remember, it has to be somewhere between negative pi by 2 and positive pi by 2, and 11 pi by 6 is much bigger than a half. It's too big. Yeah, we don't call it that. So to get to that angle, we're going to go down to this. It's negative pi by 6. That's our answer. That should have been written negative pi by 6, by the way. Don't make the negative belong to the pi. It belongs to the whole fraction. Okay, let's have a look at a couple more. That was doing sine and cosine. We didn't practice it needs secants or secants, but I've shown you how you actually get there, knowing if they're the top half or the right half. It's the same concept. What we have to look at is how are we going to restrict the graph of tangent and cotangent to know what angles we can give as answers. So here's the graph of a tangent. How would you restrict this graph to make it 1 to 1? Well, you could go from 0 to pi over 2 and then use that bit, but why? That's crazy. No, we don't do that. Why not just use all of this one arc? This is the convention. We go from negative pi over 2. There's an asymptote. It's excluded. We're going to go from negative pi over 2 to positive pi over 2, which on the circle is the right half of the circle. So we're going to see how that fits with cot. For a cotangent graph, the inverse cotangent, how are we going to restrict this graph to make it 1 to 1? We're going to use from 0, use this section of a cotangent, which takes us to pi. So again, it's going to be, we have to exclude the ends because there's these asymptotes. We're going to use from 0 to pi, just excluding those final values because there's an asymptote at them and the function's not defined for them. And look at how those words can go together. Cot, tan, exclude, exclude. That's telling me cotangents in the top half, tangents in the right half of the circle. As a short summary, oh no, we're not going to do those graphs today. As a short summary, how to remember your range of the inverse trig functions. These are your outputs from the inverse trig functions. These are your answers. The angles that come out. Cos and sine, secant and cosecant, we can include the values from, say, 0 to pi for cosine or negative pi over 2 to positive pi over 2 for sine. Cotangent, we exclude them. Secant and cosecant, in the middle, they have an asymptote that has to be excluded. We have to exclude any values from our range that where asymptotes are. So let's actually have a go at doing a couple more problems. We've got a couple more minutes left of class. Let's try some mixed up problems. Let's do arc cos of negative root 2 over 2. Remember, that's just another way of writing inverse cosine of that. And as soon as you see this, see that, you know your answer is an angle. And you just have to say, will my angle lie in the top half or the right half of the circle? Cosine is in the top half, from 0 to pi. It's going to be in the top half, so my answer must be one of these 9 angles. There's 9 possible angles, 3 quadrantal angles, 3 angles in the middle of quadrant 1, 3 angles in the middle of quadrant 2. It helps if you rewrite it the other way around. You switch over your angle and your ratio and write the regular old cosine function. I'm looking for the angle whose cosine is negative root 2 over 2. Do you remember where that came from? That's actually come from the ratio negative 1 over root 2 that's been rationalized. That's going to be easier to work with. So that's come the ratio of cosine is x divided by r. Now I hope you see that's r. That's a 45, 45, 90 triangle. And it's got to be negative. So it's not in quadrant 1. It would be positive if it's in quadrant 1. I want the 45, 45, 90 triangle that's in this quadrant. So I've got negative 1, 1, root 2. But remember what I'm looking for, because it was an inverse, I'm looking for this angle. Name that angle there for me. If my reference angle is 45 degrees, I'm looking in radians at something to do with pi by 4. In quadrant 2, that would be 3 pi by 4. Oh, 134 pi by 4. That's wrong. Is that angle positive or negative? It's positive. You're going this way around. Just because the cosine was negative doesn't mean that the angle was negative. That just told me that the x was negative. Doesn't mean the angle is negative. That is a positive angle. Let's have look at the inverse sine of 0. Inverse sine is somewhere in the right half. I'm looking for an angle whose sine is 0. Sine of my angle equals 0. That's the angle. This has to be a ratio. So put a denominator of 1. Y divided by r. Well, if one of the legs is 0, that's not a triangle. I'm not looking at a triangle. We're looking at a circle, radius equals 1. Where is the y coordinate 0? Well, here, the x coordinate is 0, the y coordinate is 1. Here, the x coordinate is 0, the y coordinate is negative 1. It's this one here that the x coordinate is 1, the y coordinate is 0. This is the one I want. What do I call that angle? 0. 0 radians. It would also be 0 degrees. Can I call it 2 pi? No, not 2 pi. Inverse sine is restricted from negative pi over 2 to positive pi over 2. 2 pi is way bigger than half a pi. Can't call it 2 pi, you have to call it 0, that angle. We haven't got time to do all of these. We could do the inverse tangent of negative root 3. We'll do this one in the middle. Tangent is right half. I'm looking for an angle somewhere between negative pi/2 and positive pi/2, and it won't be those ones because they're undefined, the tangent. I know the tangent of my angle is negative root 3 over 1, which is a y divided by an x. Must be the y is negative root 3, x is 1, y is negative root 3. Tell me the name of that angle. That's a 30, 60, 90 triangle. My reference angle is 60 degrees, which in radians is pi/3. But it's not positive pi/3 because that will be that angle there. Okay, you've got some practice on these to do. Please do some of your homework tonight because tomorrow we're going to build on what we've learned today. And you really need to practice a little bit of this on your own. Okay, I'm sorry that seemed really rushed. It seemed very, very rushed to me. Hope you're doing okay. Anybody got any questions at this point?